So today we're going to see a few applications of the static equilibrium that we've been seeing for the last few weeks. So this is specifically applied to certain scenarios, namely cables, arches, and retaining walls. So we kind of seen cables before, but this is going to go to a bit more depth. So a lot of times you have cables that are used to support or transfer loads, things like in bridges, supporting the bridge deck. We're going to assume that all the cables are perfectly flexible. So the cables, they can move based on the loading. So if I come along and add some loading, the cables can kind of move their orientation, but they're inextensible. So that means that their overall length doesn't change. And with those two assumptions, that means that the tensile force, so again, cables only act in tension, and that tension force acts along the cable, so along the same direction that the cable is going. That's kind of, again, what we've been doing so far. Anytime we ran into a cable, we would just put the tension force along the line of the cable. Same thing here. Tension force still goes along that line of the cable. And again, here, the other assumption is that the length is not going to change. So kind of the rigid body assumption, rigid body, my body's not deforming. Again, these cables can kind of deform their shape, but not their length. So if I have a concentrated load, again, we've seen a couple of these where I just have a force hanging down. That's going to change the shape of my cable. So one concentrated load is going to make my cable look triangular essentially. So again, straight line segments for all my cables. And so the tension force, again, goes along those lines. If I have several forces, then I just have kind of several different pieces of triangles. So again, each segment of my cable is a straight line between all the forces. And so again, tension forces go along those same directions. To analyze something like this, it's actually very similar to something we've done before, the method of joints. I can look at each node, and because my entire cable is in equilibrium, every node of my cable needs to be in equilibrium. So I can look at each individual little node. So look at that guy there. There's some tension force acting up in that cable along that line, some tension force acting down along that cable. And so I can find those two tension forces by using sum of forces, x, y directions, and solving for those two tension forces. And I can do that for all my different nodes and find all the different cable tensions. Another thing that's similar to what we saw for method of joints, kind of the overall. So here, the overall cable, essentially the horizontal force, horizontal portion of tension in each cable needs to be the same. So if I'm looking at kind of the reaction force here, there could be any up and down reaction force, but the horizontal reaction force FH needs to be the same as that horizontal reaction force on that side. And then if I look at kind of any part of the cable, it's going to have, again, these same reaction forces. So the horizontal component is always going to be that constant FH throughout my entire cable. So that's another way we can analyze these cables. So these are for concentrated loads. We could also have a uniformly distributed load, or not necessarily even uniformly, but just some sort of distributed load acting along the cable. So some, again, weight function varies with my horizontal distance x. This one's kind of drawn all uniform, so this one has same size arrows. That's just one example. They could be different size arrows acting all along my cable. Whatever that weighting function is, I can find the shape of my cable by essentially integrating that weighting function across the length of the cable, basically doing it twice, and then dividing by that horizontal component of the tension force that we just saw. And that essentially gives me the shape of my curve, shape of the cable. If it was this specific situation of a constant load, then that gives you a parabola. So integrating this, W is a constant. Integrating once gives you constant times x. Integrating the second time gives you constant x squared. So that's where it gets the parabolic curve. A related situation to that is something that happens quite often, and that's if the weight or the loading function is directed along the length of the cable. So as opposed to the x direction, so the previous parabola, was it was uniform in the X direction. But if you think of something like the cable itself has weight, and that weight is not directed along the X direction, it's directed along the length of the cable itself. So what's going to happen here is that when the cable's horizontal, there'll be kind of less cable per foot or per meter, whatever you want to call it. When it's at an angle, there's kind of more cable in there because it's at an angle, so there's more cable per horizontal distance. And so what you end up in that case is with something called a catenary. So this hyperbolic cosine type shape, and that is the shape of any sort of power line, any sort of telephone line that you see hanging next to the street. It'll have this hyperbolic cosine shape due to the fact that this weight is not uniform in the X direction, but uniform rather in what I call the S direction along the length of the curve itself. So those were cables. Next up, we have arches. So arches are kind of like the opposite of the cables in the sense that they're cables upside down. So cables only act in tension, pulling things from above. If you think about bridges, arches kind of do the opposite. They push up from the bottom, and their shape is essentially like an upside down cable, if you think about it. So again, they provide compressive as opposed to tensile forces. And then their shape are fixed. So the one difference, biggest difference, other than it's upside down, is the fact that an arch isn't going to change its shape. So any sort of cable, if I come along and hang a new weight on that cable, it's going to kind of change its shape and all the different angles. An arch is a solid structure. It's not going to actually do that. So that is the other big difference between arches and cables. But ideally provides an unbroken compressive path. So you have some forces acting on your bridge or your arch, whatever it is, and then those forces get transferred through the arch down to the ground to some sort of support conditions at the bottom. So because arches can't change their shape, there's something called a funicular arch. And a funicular arch is one that optimizes the load distribution. Is essentially the most efficient arch you can make for that specific loading. It's kind of like if you did have a cable and put a bunch of weights on it and then turned it upside down, that's what the arch would look like. So again, for point loads, if I had a bunch of point loads hanging off a cable, it would make nice straight lines. And so if I did that for an arch, if I have this loading distribution, I'd want to also have those same straight lines against the same angles as it would be for a cable, just upside down. And then we also saw for catenary. So if there's some uniform distribution of weight along the length of the arch itself. So again, you kind of spread these out. So they're more on the left and on the right than there are in the middle. So it's indicating that there's more weight at the steeper sections. That's going to be a catenary shape. So again, hyperbolic cosine looking shape. And so that'd be the optimum shape if, again, it's supporting something that's like its own weight. If there's something that is supporting like a horizontal span, again, like a bridge deck, then you're looking at a more parabolic shape. So that's what you've probably seen a lot if you look at any sort of old stone bridge or something. And then last up, we have retaining walls. And so retaining walls usually are built to hold back some sort of soil. And so the key here is that the soil generally can move. So if you start stacking up soil, eventually it kind of collapses and falls over. And so it's that movement that actually makes it very similar to a fluid. So if you think of a fluid, easiest thing to deal with is water. So retaining walls are very similar to dams in their in the theory behind them. And so what happens in fluids is that the pressure and therefore force increases with depth. So if you think about going underwater or even atmospheric pressure, the reason there is atmospheric pressure is because you have this atmosphere that's above you, and that atmosphere has a certain amount of weight. And because you're at the bottom of it, all that weight pushing down on you causes the pressure, which is atmospheric pressure. Same thing happens if you go out to a lake or water. You go underwater, the deeper you go under that water, the more water is above you, the more weight there is above you, and that's causing an increased pressure. And so the amount of pressure, again, proportional to depth, called H, and that's also proportional to the density of the fluid and then gravity. So density times gravity times depth gives you that hydrostatic pressure is what it's called. And so again, that's proportional to how deep you are. If H is 0, right at the very top, it's 0 pressure. And then the deeper you go, the bigger the value of H, the more pressure you feel. It also depends on the density of the fluids. Obviously, if you go underwater, you're going to have a lot more pressure than under air because water weighs a lot more. It's a lot more dense. So rho is your density. And then rho g, that's just density times gravity. That's the weight density, also sometimes called the specific weight, also called gamma. It's actually used a lot more in the imperial system because the imperial system, when you talk about density, they usually deal with weight over volume as opposed to mass over volume, just because they usually use force instead of mass. So that's used a lot in the imperial system, just gamma times H as your pressure. And so if we look at this, again, pressure proportional to depth, that means I have a linear relationship. So the pressure at the top is 0. And then as I increase, go deeper and deeper in my fluid, I have more and more pressure, and it's a straight line because of that direct proportionality. And so this leads to a triangular pressure distribution. And so because I have a triangular pressure distribution, we know how to deal with that. We know that we can replace this triangular distribution function by a single point load, 1/3 from the big end, equal to the weight, equal to the area of this triangle. So area of the triangle, I have some maximum pressure, rho g times h. And then base of this is some height h. So 1/2 base, P max times height of h. And then P max again, gamma times h. So overall 1/2 gamma h squared is the total value of that pressure force from the fluid. And then at this point, I know that point of a retaining wall is to hold back this fluid. And so at this point, I'm probably going to have some sort of statics analysis to say, is this thing going to fall over or not? So it involves taking a moment around generally this point at the front. And if this thing rotates, if it has a counterclockwise moment, that's a bad thing. That means this thing's going to fall over. It means this water or soil, whatever it is going to push over my retaining wall. If it has a clockwise moment, that's a good thing. That means that my wall is doing enough to hold back this fluid. So we'll see many examples of those later today in class. So I'll see you then.